So thank you everybody for the invitation. So my name is Mattamal. So on this talk is about robot representations for real world autonomy. That is basically a summary of all the work that I've been doing so far. So I will present some of the work that I did during my PhD a few years back, and then more of the work that I'm doing now that I'm affiliated to the School of Informatics of the University of Edinburgh. So just to give you some a bit of my background. So I did my undergrad, that is like in Chile, we have like this kind of extended undergrad that is a professional degree of engineering. So I did that and also a master's in electrical engineering at the Universidad de Chile. Then after working 1 year there, I started a PhD at the University of Oxford when I was working in robotics. I also stayed as a postdoc for 1.5 years. During my PhD, I also had the chance to be a visiting researcher at ETH Zurich. So some of the work that I will present was while I was visiting there. And now, since last year, being a research associate, that is basically another name for a postdoc here at the University of Edinburgh. Right. So just like, I guess we all know this, but just to kind of give some context. So Robotics 101, so we're all familiar here, I assume, with the Sense Plan Act framework, right? So that's pretty standard. And something that is interested about this and is related to my own research interest is that when we talk about this framework, we have certain abstractions, right? So for example, from what the robot senses, we build abstractions of the world that is basically evidence that the robot has observed or has seen, because that's used for planning. And then from the plans, we derive actions, right? So, and the plans are essentially other abstractions, but about the future. So it's like intentions, right? So all these abstractions are like all over this pipeline in like the standard, like more classical setup. Basically, when we talk about abstracting perception, we're summarizing what we know about the world, what we saw about the world, so we can have low-level representation that would be low-level abstraction. So nowadays we have all these things like dyno features, clip features, and maybe back then it was SIP features or so on and so forth. But we also we can have higher level representations that can be like a 3D map from a SLAM system. It can be a semantic map, a topological map, a scene graph, etc. Now, on the other hand, when we talk about planning, the abstractions are low level as well. So it can be a motion plan. For example, you have a lattice planner or like a motion primitives-based planner, as we have here. But you can also have a high level representation of the plans, that it can be like an MDP or like a POMDP or any other sort of like can be a graph of feasible states. So, but essentially it's another abstraction of how the robot should act. So the representations are basically like encoding this like past and future states, and that's very interesting. But one question, and one valid question, is like if we need them at all these days, right? Because we have seen LLMs, VLMs, VLAs, LBNs, video LMs. Now that we have many other things, right? So we have one large model that is basically going from sense to act, and we don't know if there is any representation at all, right? So one problem that I would like to flag here is that we still need huge data sets for this. We still might require expert demonstrations. We still need to deal with different embodiments. And some of these models, because of the previous requirements, they are difficult to reuse sometimes. So for example, in my experience now in the position I'm working, we have been trying VLAs and they don't work out of the box, for example. So it's really kind of, you need to fine tune them, you need more data, you need like kind of robot specific data and all of that. But then when we see like things now as world models, that is the other new hot thing, it feels like this is essentially a representation again, right? So because it's abstracting like the sensors, like the sensor data into some sort of like maybe not explicit, but this world model representation, and it's used for planning, for example, using MPC, as Jan LeCun has argued for, and then use that for action. So basically, we see like all these ideas coming back all the time. So in this presentation, I want to talk about representation like in a kind of a broader sense and why I care about them. So I essentially care about them because they give you explainability. So because you can know what the robot is doing, for example, and why. Because I care about modularity, because essentially we're building complex systems and we can reuse components for different tasks, for different robots is important. and about efficiency, because basically we need to deploy this on real machines and they need to adapt. I want things to adapt online with little data. So it's important to have these representations as enablers to achieve this. Right, so I will go through this presentation to kind of covering some of these key things that I consider we should care about. And I will talk about representations and action. So I will discuss some works that I've done in the past in which they connect to these things. Representations and systems. So when we're thinking about like larger scale system doing things in the real world. And lastly, about representation and adaptation. That is another set of works that I've been working on more recently. It's like basically the kind of ideas that I'm pushing for these days. So let's start with this one, that is representation and action. So basically, the key ideas here is that good representations make planning and control easier. That's one key idea that I want to give. And the other one is that they make the robot decisions interpretable, and also we can debug them, right? That is something more important from a development point of view. So to give an example, one of the main problems that I was working on during my PhD was about robot navigation. And one approach to make robots navigate, that is basically make the robot go from point A to point B, is the framework that I will present now. So there is something called teach and repeat. I don't know if you're aware of it. But it's like a very simple, very pragmatic way to make robots navigate. If we want to do inspection, if we want to do monitoring, and we don't want the robot to explore new places, we just want the robot to do the same thing over and over again because we want to measure things of the environment, etc. So basically, the framework works as follows. So in the teach step, we teleoperate the robot, and the robot will take pictures of the path, right? So it will move, it will start like taking these pictures, and we'll place them in a graph. Then it goes to the end. So we're teleoperating the robot all the time here. So each node has the pictures, as I mentioned. And then when we want the robot to navigate, basically the robot will take a new picture, it will compare them against the map, and it will try to figure out where it is located, right? So the question is, am I in the same place? Maybe yes. And then if it's yes, I will try to move to the next node, and then it will look slightly different. So then I will try to correct it. And then basically the robot, by just repeating this process all the time, it can kind of replay the same path that I was taught to follow at the beginning, right? So it's pretty convenient if we want to do inspection. So in the first part of my PhD, I was working on this problem, but I also like kind of give it a twist. So I was like thinking about what if the robot has more cameras? Sometimes just looking forward is not the best thing because you're looking at a white wall, and maybe if you were looking like at the back, actually, it could be more useful because probably you have like some features that you can use to track all the time. And one of the things that I did in this first piece of work that was published in ICRA in 2021 was about how to make the robot actively switch between these cameras to use information that was more interesting. So here you will see an example when we're teaching the robot that trajectory using the data from both cameras. So you see both cameras now, and now the robot is switching. So sometimes it will go to from the blue to the yellow/orange one because it's actively switching depending on which camera was more informative. So we also deploy this in more like kind of realistic settings. So this is like one area close to the university in which we were like kind of introducing all these kind of cases in which we were occluding the camera, so forcing the robot to switch to the other one, but still like staying on track. And the robot like made like very successful trials here. I had to say that back then, so this was 2021, it was with this robot called Animal B from a Swiss company called Robotics. So this was like a big mission to me. It was maybe like 45 meters of the robot walking autonomously. But then you see things that robots can do now, and maybe it was not that much, but it was a big thing back then. So one problem of this, though, as you might realize, is that the robot is really good. It can follow the path. So the path, if somebody was like teleoperating the robot before, the robot, essentially, the path the robot needs to follow is collision-free, right? Because we will not teleoperate the robot to hit things or anything, but it might be the case that the environment can change. And if the environment changes, maybe something is occluding the path, maybe somebody puts some new object. So this representation that is purely topological, actually topometric, but we can discuss the details later, it only encodes this free space, but it doesn't have any notion of what's around the robot and how the robot should navigate safely, right? So in all these legged robots, so they rely on depth sensors that they have like all over the body to build local maps of the environment that they're used mainly for locomotion. And here we were using them for navigation. So the environment looked like this at the beginning, just using that. But then once we add this local map, the environment actually reveals all the geometry around the robot, right? So, and this is like a rolling map. So it's moving with the robot. So we don't need to store the whole map. The only thing that matters is what is around the robot. And what I did in this work is that I propose a local planning system that is essentially reactive. It's just like, you can imagine that it was like a artificial potential fields based planner, but this was like one step more, adding like some conditions on the state of the robot, how close it was to the obstacles, and it was kind of defining which potential fields were more important to some extent. So the framework was called Riemannian motion policies, if you're interested. I will not give the details. Maybe we can discuss it later as well. But basically it was one way to generate this reactive motion just from online data. So here are some examples. So for example, if you see here, the blue line is the path that the robot was taught to follow. And then we added these new obstacles on the way. So the idea was to force the robot to deviate using this reactive layer. So here the robot is doing everything autonomously. And so we place some objects. Of course, this is like an artificial setting, right? This was in the lab, the same lab that you saw in the previous video. But was to make the point that the robot now was reacting to what was in the environment while still relying on the high-level plan that was taught by another person. And things got more interesting when we later deployed the robot in an underground mine. So because back then, around the time we were developing this period, we were part of the DARPA SAT challenge. So we were like deploying the robot. You see here, this was basically a mine somewhere in England. And we're doing these underground experiments. And all of this, you see here is the robot following the path autonomously. Now, this was like a much longer trajectory than the one that I showed previously. And for example, here the robot was completely losing track of the visual features, but it was relying on this reactive layer to avoid the obstacle while still like using odometry information to follow the path and then kind of resume when it was able to track features again. So all of this was autonomous. Now, in this same space of like representations for action, so one work that I've been contributing to, so this is by one of my colleagues, Aditya, that works here in Edinburgh. So he's a PhD student, and he was looking more into manipulation settings, so insertion and this different space of problems that I never worked before. But he was like tackling them from the perspective of the representations. So in this case, he was building probabilistic maps of, for example, was an insertion task. So it was building a probabilistic map of the hole where he wanted to insert something. You can imagine like a key, for example, or a USB stick. So he was building this map, and then it was probabilistic. So in that way, it could guide him about where was the best place to kind of gather a new data from. So what you see here on the right, so you can see my mouse, right? Yeah. So
Yeah.
So you see that part that looks like brighter has higher uncertainties. In that case, this information that was encoded in the map was used by the robot to poke and probe that area, and then it would gather new information of contact and vision in order to update the map. And in that way, it could kind of efficiently explore the space in order to reconstruct the target hole and then like kind of attempt an insertion. So this paper was recently accepted to IROS. So it's going to be presented in October, November, I think. And we still don't have the version on archive, but it should be updated in the next few weeks. So in the second part, I would like to talk about representations and systems. So why do I care representation in this context? Because they enable modularity. So we can basically, they act as a common interface for different applications. So when we're building this very complex system that needs to do autonomous missions, like in the wild, so it's useful to have this representation that can be reused, or maybe we can interpret as humans and so on. So one of the projects that I was involved in while I was it was in the last years of my PhD when I started my postdoc in Oxford, was in this project exoskeleton navigation. So it's kind of a different space, but just to give you the context, so we were collaborating with this company called Wondercraft. So probably you remember the Olympic Games that happened in, I think it was in 2024 or 2025, 2024 in France. There was like at least one footage of somebody on an exoskeleton carrying the torch. So that exoskeleton was one of the ones made by this company. So we're collaborating with them because they were interested in adding environmental perception. So, for example, if you are the person that is wearing that exoskeleton, you need to drive it yourself. So sometimes it can be like very exhausting from a cognitive point of view to kind of be very careful about how to drive it, because basically you are driving your own body, right? So so we're like exploring ways in which we could add this environmental perception. Maybe not, it's not something that's going to be deployed on an exoskeleton now, but maybe in the next few years, maybe it could be something that could happen. So this work was led by this other PhD student in Oxford called Janeng, and he published this work also in Robotics and Automation Letters 2025. So this is an example how the system works. So this is like an integrated system. So it involves like the odometry estimation, that it was using the sensor that I didn't explain, but basically we developed this sensor payload that you could attach to your leg or you could attach to the exoskeleton. And it was running odometry and SLAM algorithms on board. Because the idea was to have this single unit that we could kind of swap and place and test in different conditions. And we didn't want to have like a camera that was on the head of the person or on the body, because it could it would be something annoying to carry one, or the other one could be that if you are manipulating things, it is easy for you to kind of occlude what the camera is doing. So we wanted to place it in a kind of an unconventional place, that in this case was the leg. So what you see here, some examples that we did with somebody carrying the device, because we didn't access to the exoskeleton when we were developing the system. So here is running a visual inertial odometry system, plus a local mapping system that produces like these local patches you see here, and all of this integrated into a semantic SLAM system, where each of the nodes denotes a color of the room. And the idea is that by combining all this information of the geometric terrain information with the graph, we could build these multi-level terrain maps. And here we're showing how it works on the exoskeleton. So because eventually we went to the offices of Wondercraft and we work with them to integrate this on the exoskeleton, and we show this with a dummy. So you see the exoskeleton is moving because it's being teleoperated, but it also carries our sensor payload, but it's not somebody driving the exo. But it's kind of showing the same things that I was illustrating in the previous video, but now integrated with the exo, just to give an idea of how the system, even though the robot was moving very kind of, is aggressively moving the legs. It also, the motion is not like as we walk, so it's like a bit different because it's like a mechanical system, right? It still is very capable of tracking the state of the sensor, as you can see on the map here. And reconstruct the local terrain that was integrated into global maps. Right. So, right. Now, the other project that I wanted to present in this space of systems. So during the last bit of my PhD and also my postdoc, I was part of this European Union funded project called DigiForest. So the idea was that there are many, so foresters need to build this, they need to manage the forest, and in order to do that, they want to get like precise measurements of like how many trees they have, what's the volume they have, what the structure, like kind of the family structure that the trees have in the forest. Because, for example, in countries like the Nordic countries, as in Finland, they are concerned about doing kind of sustainable forestry. So in that case, they don't want to cut all the trees in an area that would be a clear cut, but they just want to cut the ones that basically supply the right demand they have, but also without affecting the ecosystem that much. So you're trying to leverage all this knowledge that you can extract from the forest in order to produce the best basically supply the amount of wood timber that you need, right? So the thing is that most of the operations here, they vary. So you can have drones that fly over canopy, building these 3D maps from above. But then actually you want to have like more fine-grained information, for example, like the diameter of the tree sometimes is difficult to see from above. So you need to go and do manual scanning. So with these big TLS, terrestrial laser scanner sensors, or sometimes you can even do manual manual measurements with the tape. So all of this is like very expensive and time consuming. So the idea of the project was to develop like this team of heterogeneous robotic systems that basically could gather information at different levels. So you could have drones collecting data from like kind of at the canopy level, legged robots, or maybe sensor payloads carried by humans that could kind of gather under canopy information. And the idea was that we also wanted to have an autonomous harvester that was exploiting all this information, that was integrated into a support system that will help you decide which trees you want to cut. And then this big harvester will go and cut the tree, exactly the tree you wanted. So that was the vision of the project. So yeah, so you have like this particular, you have like this over canopy drone, that this was a big one that could cover like hectares. And then we have a bunch of different terrestrial platforms. Like we have this under canopy smaller drone, like the Leica one, because we were also collaborating with Leica. We have this sensor payload that was developed in Oxford that we call Frontier. And we have the animal robot as well. And lastly, we have this harvester that was this big machine that one team of the consortium was working to automate and kind of give it perception, 3D perception and autonomy. So this was like, for example, one of the field trials we had, just to give you a scale of the big robot. So the thing you see here on the back, that's like the big harvester. So we have the legged robot here, and this was like part of the team that was in that field trial. Yeah, so on our role in Oxford, and particularly my role, so I was leading the development of this system so we're envisioning this system in which we're exploiting legged robots to do forest inventory. So because legged robots now, you can see them like now you can see quadruped robots doing pretty amazing things, humanoids. So the question was like how far we can go with a robot doing this sort of tasks. So particularly we're like focusing on addressing three main problems. So one was state estimation in the forest, autonomous navigation, and also we wanted to do online forest analysis. So we wanted to provide measurements of the trees, like for example, the diameter at breast height, that is like roughly at 1.3 meters, and all the trees that were like present in a certain forest plot. So here the system is more complex. So because we have different sensing units, we have an operator that also instructs like the high level plan. So when we start looking at the details of this stack, then we start seeing that there are all these sort of intermediate representations. So we need to estimate poses, we need to estimate terrain maps, we need to estimate dense maps for other things. The plan itself was also sort of a representation of what we intended the road to do. So, and basically these are like the interfaces that make all the whole thing, that orchestrate the whole thing. And here I can show you some examples. So we did deployments of this system in 3 different countries. So we tested it in the UK, we tested it in Finland, and also in Switzerland. So, and this was a development that happened over many years. So when probably we started it roughly in 2023, then it was deployed in, no, even before, I would say. So this was 2022, 2023, and the last ones were in 2024. So, but these were large-scale deployments that we did with this robot. So all the videos that I will show here are autonomous. So the first one here is in Finland, in which we're mainly testing the autonomous system. So here, the team, including myself, were standing at the beginning of the sequence, like somewhere like here behind the view. And we just like let the robot walk. And because the idea was that we predefined like some kind of inventory mission. In this case, the robot had to follow this red path that is kind of, there's like an offset in the z-axis. And then the robot was like trying to follow all the waypoints there and building like this, the map of the environment. And the idea was to extract the trees as well. So at this stage, we didn't have the tree extractor system integrated because we're mainly testing the autonomy. But this is like one of the examples. So we have like this video of all the missions is like 30 minutes long, if not more. And you can find it available on YouTube. I will just show you like the main results. So because this is like a very long, we made this video without any cuts just to show what the robot was effectively doing, because that also gives you an idea of the challenges that the robot can face. So this was the largest mission we did. This was in the Forest of Dean in England, near Wales. This was 120 meters deep. So along this axis, that was 125 meters. This was maybe like 40 meters or so. In total, the whole area, considering the LiDAR range, covered like a hectare. And this was when we integrated the forest inventory system. So you will see that as the road is walking, it's like reconstructing the ground that is like the mesh you see here. But then you also start seeing the trees popping up because it was segmenting the trees from the point cloud that was accumulated when it was walking. So this is like just a recording, a Rosbach playing of the thing that the robot recorded. There is no offline processing here. There is no external computer. All of this is running on board. So I will speed up a bit to give you, because the mission is very long. There were some parts in which we had to intervene the robot, of course, so we analyzed all these things in the paper. But basically, the idea here is that the robot is doing this tree segmentation as it walks, and basically, when the robot finishes the mission, it can provide a spreadsheet with all the trees that it detected, where they were with respect to the some frame that we chose and the diameter of them. So we also tested it like in other more complex environments, like these forests near Oxford. So here it was over the summer. It was a different kind of forest. So here you had like a mixed forest. It was not just conifers that are like pine trees, but also you have like other kind of deciduous trees that are like have different structure, more difficult to segment. But it's also showing how the system works and how the robot like struggle in some cases to also walk in this environment that reveals some of the challenges for locomotion, navigation. That is all that we discuss in the paper. So the last straws were into the land. So something that we did here is that, unfortunately, like as we were moving towards this from the winter to the summer, when we were doing these experiments, the terrain became more challenging because you have high grass, then things are more difficult to describe because it's not just the geometry is not enough to, for example, to characterize where you can walk and where you cannot walk. So yeah, but it was a very interesting project, and I'm happy to answer more questions about this if you have them later. Yeah, so that leads me to the last bit of the presentation, in which I want to talk about how you can use this representation to make the robot adapt online and change their behavior. And here's some points that I would like to make is that nowadays we see like all this rise of pre-trained models, right? And you have things like Dino, you have things like Clip, and also you have like other models like feed-forward reconstruction models that are also getting popular these days. And I personally think that they provide like some very useful, reusable low-level representations that when you wrap them around high-level representations like graphs or other structures, you can achieve this scalability and adaptation that maybe even though the model is pre-trained and you don't need to fine-tune it, you can still exploit this to kind of achieve other things. So the first work that I want to show in this space is called LexCSG, that is was developed by my colleague Christina. There's a finishing PhD student in Oxford. So this was one of the last works that I was involved in when I was there. And basically the goal was to build scene graphs. So a scene graph is this representation that is hierarchical. So you can have like a layer that can have the 3D geometry, another layer that has the semantics, another layer that encodes which rooms you have, and then you can go to a building, and then it can be like go up and up. And one of the things we want to achieve here is I wanted to do this just from vision, because sometimes you have different sensing modalities. You can have glasses now, you can have a camera in your phone, and you will not have a LiDAR everywhere, even though it would be very convenient, for example. But it was interesting to explore how far you could get just using monocular cameras. So, and she was showing here like how to build this, and the key idea is that it's exploiting this this knowledge encoded in pre-trained models. In this case, it was models such as Dino, such as Clip, and also these feed-forward models that provide the geometry of the environment. And some key ideas here is that this is really exploiting semantic information to guide the reconstruction. So this is not just like applying a feed-forward model, like map anything here that it will give you this reconstruction, but it's using semantic information to know that all these images that are passed to this model belong to the same room. And in that way, you know that you can guide the model to provide better reconstruction, because if you just run it passing images, just a bat of images one after the other, the reconstruction will not be as good. So here, by exploiting the semantic information, you're able to kind of guide the reconstruction and achieve like more like better room level reconstruction that overall they look better when you put them in context. So I will show you some examples here of the reconstructions that we can achieve. Sorry about that. Yeah, so these are like some qualitative examples of the reconstructions. Of course, you see some artifacts in some cases, but I think it's pretty nice considering that this is just using monocular data. Yeah. So in the second word that I want to talk in this section is online learning. So when I visited ETH, I was working with Jonas, my colleague that was doing a PhD there. And we were thinking about this problem that I presented briefly when I was talking about the forestry work, that is about knowing where the robot can walk. So that problem is called traversability estimation. So basically, you want to know where the robot can navigate, right? And for that, you need to consider the capabilities of the robot itself, but also how the robot perceives the environment. So it's like a mix of things. So it's not just like semantic segmentation of the road, but it's also taking into account some of the knowledge about what the robot can do. Because, for example, if you have a small wheel robot, and you go into a grass field, it might be stuck and maybe will not know where to go when the grass is really high, because it cannot see anything. For the legged robot, for example, it was the same thing. You will see all the grass just like us. From the lidar perspective, it will look like a bunch of obstacles. But actually, the robot could walk there because it has legs, right? So the idea was like how to encode that information in a simple way so the robot could walk in these environments, even though we didn't have to train like a new classifier for that. So our approach was, let's just make the robot learn online. So if somebody shows the robot that it can walk on grass, then that should be enough information for the robot to integrate and then navigate on grass. So how we implemented this? So basically here we have an online learning system. So I will show this video. You will see the robot, as the robot is walking, is collecting images, and then it's storing them here. So it has like this sort of history. And also, while it's walking, it's also producing this sort of projection on the ground of the areas where you walked before. So it's like a footprint, like an extended footprint of the areas that the robot has walked over. And then, sorry, I keep pressing the slide. Yes, so while it's walking, it's collecting this data all the time. And then what we do is that we train some system in which we use this path, this strip you see on the back, to self-supervise the vision data. So basically, this strip that you see here tell us where the robot can walk. So if we have an image from the past and then we see this strip overlaying here on the image, then we can know that that was an area where the robot can walk. And basically, we can use that information that we generate as the robot keeps moving to generate supervision signals to train a neural network. So here you will see that this is the prediction that the neural network provides. And at the beginning, the light blue means that it's unclear. When it gets blue like this one, that means that it's confident that it can walk there. And when it's red, it's confident that it cannot walk there. So you will see that as the robot keeps walking and is collecting data and running this learning system, then it starts adapting. And then you would see that now, since the robot walk on this grass, then all the future grass that it has ahead looks traversable, because it's really exploiting this information from the last few seconds to keep training this prediction. Like it's like a semantic segmentation, but this is just more binary, saying that I can walk here, I cannot walk there. So the interesting thing is that all of this was trained and tested on board as well. So we had like a mobile GPU, and there is the whole learning and training system running there. And basically, we could just like bring the robot to the park. For example, here you see Jonas like driving the robot around. So it was the first time they were bringing the robot to the park. And after he made it walk for a few seconds, you will see that this is like unclear what is traversable and what is untraversable. And as the robot starts training, because it had enough data, it will start propagating the labels forward. And then it will predict that the terrain in front of it was traversable, even though it has not walked there.
Can I ask a small question, Mati?
Yes.
Did you experience any challenges in this work when the robot changed in terms of lighting conditions?
Yes, so that's a very good question. And I would say something that we did here that was basically one way to tackle this, even though not directly, is that we use dyno features to learn. So I have nice visualization about how this is trained. Maybe I can show them later if you want. But basically we extract dyno features, and we use the dyno features to train this regression model. So I would say that some of the lighting conditions where we cope with them by using the sorry, let me frame it again. So because we use those features and the features were robust, we could deal with some of the lighting conditions, but we didn't address the lighting conditions directly. So I would say that if it's fully dark, it will not work anyways. So but the features were actually pretty solid in this domain. So I would say that you could test them depending on the application to see if they work as well. But for example, to provide these sort of regions that belong to the same semantic classes, even though you didn't know the semantics, they were pretty good in our experience. But I don't know if that clarifies some of the questions. Or...
Yes, thank you very much.
Yeah, if you want to know how it works like in more detail, I can show like the other visualizations I have. But I think I will continue with the presenting these topics, and then we can kind of extend the discussion. Yeah, so the work that I'm doing now is slightly different, but also related, I would say. So because before I was working more on navigation, but there were also some applications in which we were trying to assist people in certain ways. For example, the exoskeleton work. And now that I'm part of like this new Center for AI and Assistive Autonomy, we're looking into how we can build AI robotic systems to help people in different ways. So we have three main strands of work. So one of them is driving. So not to develop autonomous cars per se, but to develop assistive systems for the cars so they can give you advice on how you should kind of park, or like they give you advice on be careful with certain things. So we're interested in that strand of work for the driving case. We are also working on surgical applications. That is like a completely different one, but it's more about how you can assist surgeons or how you can develop medical robots to assist medical teams in different things. And we also have a care and assisted living strand. That is the one in which I'm involved now, in which we're looking into applications of robotics for daily activities. So for example, when you're cooking, when you are like doing things that you need to eat, and maybe there are different ways in which robots can help you in that case. So to give you some motivation, so when you are cooking, probably we didn't pay much attention, but there are many things that are happening there. So we're doing some planning because we're following a recipe, or maybe we're just following by heart, and then we remember the steps that we need to follow in order to complete the dish. So we need a spatial memory as well, because we need to remember where the ingredients are, where we have the stuff in our kitchen, like utensils and all of that. While we are doing the things, we also have like a lot of sensory motor coordination. So if you need to steer things, so we need to hold like the pan, we need to move the spoon or whatever. That also requires physical strength, right? So if we need to lift the pan and move it somewhere else, we need to say carry, move things around. So there are all these things that probably we just overlook. But then there are different conditions that people can develop, and basically that impede them from achieving this. So for example, you have ADHD, you will not be able to follow the plan closely. If you are developing dementia, you will have problem to remember where things are, so your spatial memory is failing. If you have like any motor control disease, you will not be able to execute like the sensory motor loops that you will need to do to steer, or if you cannot just lift things, right? And you have any sort of weakness. So we are looking into how robots could help you in this thing. So and one of the problems that I'm looking into, the more like if we approach it to robotics, is like how robots can help humans. So you can hand objects or tools. So here cooking, you might need like like the knife that is over there, like, or maybe a ball. Maybe you want the robot to help you rearrange, so you need to rearrange the space, reorganize things, or clean it up after cooking, or you need to wipe things. So that's one way in which robots could help you if you're not able to do all these things by your own. But in order to do these things, there are like different questions, right? So if you need to hand objects, you need to know the objects. If you need to know where to find them, for example, and you also need to know how to manipulate them. So there are like many open questions here. And particularly, I was like thinking about these three problems. So one case could be, say you say pass the bottle, and first it was a Coke, but maybe the bottle could be a different bottle. So it's the same setup, but maybe the bottle changed because maybe it's the bottle from somebody else, or maybe it's like a different drink this time. You can also ask the robot to give you something that is not within the field of view, or you could also ask the robot to pass things that maybe are hidden. And in solving all these problems, you need to address different things. So that requires spatial and semantic memory. So for example, you ask to pass the bottle and now it's a different bottle. So the challenge is how do you generalize the behavior across objects? So if you're thinking about give me the apple, then the problem is like short-term memory, right? Because maybe you saw the apple 2 seconds before, but now you don't see it. It's not within the field of view, but you need to remember that the apple was there. And if you are asking like pass the salt and the salt is hidden, then it's more like a long and short-term memory problem, because maybe the salt was there yesterday, but now we have this new ball that is in front in this area. So maybe the salt is still there, but you don't know because you cannot see it directly. So, but all of this requires, I would argue that it requires some spatial and semantic memory. So the work that I'm doing now, this is very kind of active work. So there are not many results in this space. So there's ongoing work. So what I was looking into, like models of how spatial memories work from different contexts. Particularly, I was looking into neuroscience, cognitive sciences. So for example, there are very interesting ideas and models from many years ago. So Tolman presented this thing called means ends fields that was used to explain how rats navigate the environment. And there are like newer things developed by other people. For example, this other model called Tolman-Eichenbaum machine that tries to explain relational associations of different kinds of knowledge. That could be space, that could be concepts. So there are like many different ideas that are not in robotics, but that people are developing in different fields. And it's interesting to see how they could apply to this setting. So something that I'm looking into is like how we get this structure from robot experiences. So working in this manipulation context, I've been looking into data sets that do this, where we have this more challenging sequence that involve manipulation, that involve moving around. So there is this data set called Epic Kitchens, that is monocular egocentric video. We have Libero, that is another simulated benchmark. And basically, you have all these data streams, right? How you make sense out of them if you're not going to build a map in the same sense that I presented before. So one of the things that I've been looking is like how you can learn latent representations of these experiences. So for example, this is a 2D projection of one experience of Libero. And something interesting here is that these different kind of egocentric snapshots, that this was all learned, it has some structure that I'm like analyzing now. But for example, one of the frameworks that I'm looking into gives you some tools to do planning in this latent space. So for example, if the goal is this image that is here in the middle, then this, for example, representation that I'm looking into gives you a rule to move from any state that you saw before to reach this one. So the arrows you see here, when they are darker, they are like stronger directions in which you should move in order to reach this target goal. So for example, you see that the target goal has like light blue ones, because it's basically like the end goal that I want. But any other state is kind of pointing sort of in that direction. So if I'm here, the arrows are pointing to the left. If I'm down here, arrows are pointing to the up and left. And if you are here, the other way. Then if I change the goal, then I get behavior, at least from terms of like these directions, that it's kind of guiding the behavior in the right way. So the same if you put it down here. So this is ongoing work, as I mentioned. So I hope to have like more interesting results demonstrated on a robot doing more interesting things in the next months. But this is like what I'm thinking about now in terms of representations. And the idea is that eventually, like in the context, like the more general context of the center, is that we want to test this thing in realistic scenarios. So we were developing this kitchen mock-up in the lab we have here. The idea was to have robot arms, to have different sensors that can measure signals from humans. This is a work that we're doing with Hiram, that is a PhD student here. And now we have the kitchen built. So it's exciting to see what things we can do with this one in the next months. So yeah, in summary, I think I'm wrapping up now. So yeah, hopefully that I gave you like some glimpse on why I think that it's still important to think about representations, because they enable action, they enable building these complex systems, and they also like give you some ideas on how you can make robots adapt, even though the robots are experiencing new things that probably they didn't see during training. And you're interested in more of these topics, so I highly recommend you this book, that is a SLAM handbook that should be available in the next few months. So I was lucky to be part of one of the chapters. So I contributed to that chapter on legodometry, that is how you estimate like the self-motion of a legged robot, because this is about SLAM, that is mapping and localization, but there were like many chapters, and one of them was about legged robots. There was this one, but other chapters that could be of interest to you also. There's visual inertial odometry, LiDAR, semantic maps, and many other interesting topics. So yeah, so that's everything. So you have any questions, I would be happy to discuss a bit more.
That was an amazing presentation, Matthias. Thank you so much for taking the time
Thank
to
you
do
very
that.
much.
And I have a bunch of questions, and I presume that most people also have questions. But before that, I want to first apologize for the initial disorganization at the beginning of the presentation. There was some miscoordination between parties. So now that we are past that, as usual, for everyone that wants to make a question, well, it's somewhat close-knit at this point, so we can probably just raise our hands. But I'll start. And I guess I'll start asking questions going backwards, because I have questions all the way back to the beginning. So you were talking about latent representations. And I actually wanted to ask you about the prospects of planning and control in latent space. I've seen works on the matter. Naively, I would expect that you need certain properties on the embedding for that to be possible. I would expect that the projection that takes you from the real world to this latent space has to be diffeomorphic, so that you have the nice properties that allows you to I don't know, try and do MPC on that space. What have you seen based on related works and on your own work?
Yeah. Okay. So just to clarify here, like I still need to see if this thing works in this context, because I would say
really
in terms
promising.
On the formulation, I would say that it looks like JEPA, if you have seen those works.
Yeah.
The formulation is like that, but I'm using simpler models. So I'm using linear models, because I think that even though I'm using like this, I'm trying to see how far I can get with this. I still have like that background that I presented before that is more like traditional. So I really want to see like that connection happening. So I guess that the part that is appealing to me from the formulation is that I don't need to engineer like this whole system that has a front end, a back end, extract features and all that. Maybe I'm still extracting features, but maybe from the point of view of how the representation is structured is appealing, because if I want to add more data later, I can just use the same process, right? But I could say that here, the way the formulation is developed, you have one latent state that encodes observation, and then you add like some term that is the action. So I would expect that it should behave okay-ish. So in the examples that I've seen in simpler settings, it works. But of course, like I'm pushing it like really far here to have like high dimensional input. So I would say I wouldn't confirm anything at this stage. I hope that it works. And if it doesn't work, maybe I will go back to more traditional things. But it's kind of the question that I had, right? So it's like, because I know that if I just build a scene graph of the kitchen, it will work, right? So, but I didn't want to do that. I just wanted to test something new, because with the potential advantage that I could extend it faster as well. I mean, in a more flexible way. So
Right.
yeah, so we'll see. I mean, you will see this out, or if you don't see it out, that means that I'd failed, right? But I'll try something different.
Yeah, yeah. I mean, I find it very appealing too. I mean, if it turns out that it works, like being able to use all the techniques we've known about for decades that we can prove optimal on this higher dimensional spaces without having to deal with that projection. Just learning it end to end. That would be really cool. If that was possible. I see questions coming up.
No, I think it was Ignacio that needs to leave.
He had to leave. He had to leave. Okay, then I'll go to my other questions. And going backwards. When you were discussing I think it was while visual navigation, where you had the self-supervised training. Was the initial traversal teleoperated, or was it fully autonomous?
The first one is always teleoperated.
Oh, okay. Yeah, but because I was wondering how do you avoid the overfit if you're
no. The first one. So I think that's kind of the assumption that in this case we're not telling the robot explicitly you can walk here and you cannot walk there by labeling images, but it's like by driving. So it's like at the behavioral point of perspective, you are teaching the robot what it can do, and then it's extracting the features from the environment that kind of.
And did you have to do some sort of contrastive learning? Like if you teleoperate to a place where the robot cannot really like hold or it fails, how did you handle that? Or were you teleoperating away from those places?
Yeah, so I think that's still an open question, and I would say that if I need to do the work again, that's one of the hardest things, because now what we use as a supervision signal was like how well the robot was tracking the velocity command that we were sending, because we were saying move at 30 meters per 30 meters, that's too much, 30 centimeters per second. And then we were getting from the state estimator what was estimated velocity, and then we were like comparing the difference, and then using that, mapping this into a signal that we could maybe more like a score, right? Now, I think that was probably the worst idea we had in the paper, and but at the same time, it was the best idea we had in the paper, because every single time people ask about this, so there are always questions about the work. But yeah, so in principle, if the robot is struggling, it should fail to track the velocity command, but yeah, I think it's still like two cores. I think that probably if you want to solve the problem with the legged robot, you need to have like finer information, like for example, forces or sensors at the feet, or maybe around the body, like something like a skin, something like this, because I think that it was very tricky to solve it this way. And I think it's very simplistic. So I think the goal of the paper was not really kind of showing that we could solve that one, but that we could do it online, and kind of it was easy to. I think that was the main contribution, but I would agree that that's a limitation. There are some follow-up works by my colleague, by Jonas, in which he was trying to estimate terrain coefficients, like friction, stuff like this. Yeah, but that's another piece of work.
Super interesting. Rodri?
Yes, there is a question. Yeah, I had a question about the same issue that Michel talked about, how you encourage, or how you do that the robot pass through a high grass. You already respond that there is teleguided. So, but how you explain to the robot that do not pass over there? I mean, the opposite learning. I mean, don't pass over this part of the track.
Yeah, so I can show you an example of that. That's a very interesting question, because I mean the framework allows you to do this in a very simple way that is almost too naive, I think. But let me show you what we did. So if I show you, this example. So basically what we did here is that we wanted the robot to follow the path without getting into the grass. So that is kind of what you are asking. So basically you just train the robot to walk on the path yeah, something that I didn't mention is that by default, everything else is untraversable. So it will avoid the grass just because it never walked there. But the moment it steps on grass, it will learn that. So one way to avoid it would be just not to train to walk on the grass. So here you will see that we are just training the robot to walk along this path. And then all the grass will appear as red on the right-hand side here. Because the only information that is getting that is traversable is the path, is the footprint that is projected on this path of dirt. So, and then we could deploy the robot autonomously. So here we stop learning and then we just let it run, staying on the path, because it was trying to avoid everything that looked red here on, as you see on the visualization. So yeah, you see that here, all that is blue is where the robot will try to walk, and everything that is red it would avoid, because we just train it on the blue things. So I don't know if that clarifies the question fully, but
yeah, perfect. Thank you very much. Amazing
no
work,
worries.
amazing presentation. Thank you.
Thank you.
Really, really good. We are 4 minutes over time. I still have questions.
Yeah.
Do you have time for them, or do you need to leave?
I do have time. This is the end of the day here, so
Okay,
yeah,
cool.
I have some time if you want to stay a bit longer.
Cool.
Yeah, because
So the forest. The thing I found the most interesting is that you were talking about, and I don't know if the project eventually made it all the way there. You were talking about like multi-robot environment representation building, and in like it is my understanding that in like forests or places where you have like a dense canopy, you cannot rely on good old GPS signals, at least not consistently. So how did you manage? How do you manage that fusion eventually? Was lighter inertial slam enough? Yeah, how?
yeah, okay. So there are different things here. So the drone that was flying over canopy was just using the default software from the drone, so you can just send waypoints and it will just track them, right? It will give you the map and you just like offload it. So there was nothing we could do about that. Everything that was under canopy, yes, the GPS was a problem. So usually what we did is that we would initialize SLAM systems when there was like a clear area. You will initialize the SLAM system to get that GPS, but then all the estimation was happening in the SLAM frame. So the GPS was only added in the end. We wanted to fuse everything. So so from the robot's perspective, it's always operating in the frame of the SLAM system that was running. But each robot was running a different SLAM system because they were developed by different research projects. So at some point, we wanted to do is like do this merging of all the information collected by the robot, but we had to define some standard. And in this case, we defined missions that were defined by nodes, and so sort of like this graph, and then you will have the point clouds attached to the nodes. And then there was an offline pipeline that we developed. That was actually something that other people did in Oxford that will fuse all of this using kind of LiDAR place recognition systems that will find the matches. And then it was doing this multi-mission merging of all the missions. And then that would be combined also with the aerial data, but we have a paper on that I help in that paper, but we try different approaches there. But it's kind of similar, but you have to find features between point clouds obtained from above, point clouds obtained from below canopy. So the ones from below canopy will not see the tip of the trees, while the other ones will see like the cone of the trees. So we had to kind of do this sort of like a point cloud alignment, just extracting the estimated center and then try to find a match. And then all of that was combined using a factor graph similar to SLAM, but offline, finding all the... And it was an interesting work, but it's more engineering in that sense.
Yeah. Okay, but like you were merging through LiDAR place recognition, not relying on GPS anchored.
No, in our experience, at least when we're doing mapping sessions, it was very unreliable to rely on GPS while we were in the forest. So we will try to catch it at the beginning. And then that could be used to initialize the global frame. But in the end, it's just a transformation, right? So
Yeah.
I know that, for example, for the harvester, they were relying more on GPS, but the machine was larger and the forests were sparser. So in that case, you could get still like some. There are very impressive videos from these people because it was a collaboration from ETH and the Finnish company, and you see this machine driving autonomously in Finnish forest, and it's very cool. But also, like, the Finnish forest had 5G, so I guess that they also had other advantages there. So.
Cool. Okay. We're talking about that. Yeah. At the beginning, you were talking about geodesic distance fields.
Oh yeah.
And remote control.
Yeah.
I want to ask about those geodesics.
Yeah.
Like, how are you computing those?
Yeah.
It tends to be like, if I might be misremembering, but even when you're dealing with like standard Lie group algebra, there are no closed form algorithms to compute those geodesics. That you need to rely on numerical methods. I might be misremembering. So how was it efficient? How did you manage to run that?
Yeah. So I think. So we call them in the paper geodesic distance fields, but in practice, what is happening is that you have, say, like a binary map, and then you set the goal. So you know the goal, and then you use an algorithm called the fast marching method. That is essentially like something like solving the heat equation. So just like you have a source of heat, and it's like kind of propagating. And basically that naturally gives you like this sort of geodesics to any point in the map.
See.
And then basically you do the inverse thing, that you start from where you are, that the road is in the middle, and then you have a gradient that tells you how to get from there to the goal. So then you could, at any point you could be in the map, you could know what was the direction you should move in order to reach the goal. Now, if that is...
And those geodesic curves were like in 3D, or were in like full 7 degree?
No. This is just 2D.
Oh, 2D.
So,
okay.
Yeah,
I thought it was like 3D plus orientation.
No. No, I mean, from the... Yeah, okay, it was good to clarify. So from the navigation point of view, the problem is really simple. It's just like planar motion and rotation, right? So I don't think you need to do 3D... full 3D planning, or like even higher state planning with the legged robot, because the locomotion controllers are so good these days that you can just assume that the robot is going to execute. So I would say that if you want to push the argument, basically for the robot, the word is planar, right? So because even like some of the controllers, they can go under obstacles, above obstacles. So if you say move forward, the thing will just do something, right? So then for a planning point of view, I think that it wasn't we were just solving the problem in 2D. So the idea was to get like the rotation and the angular velocity and the linear velocity from that.
So 2D on the traversal map, the traversability map.
Yeah. So then the fields that I got were 2D arrows that basically I mapped to using this Riemannian motion policy framework to commands that would be in the base frame.
I see. All right. Understood. Cool. Still. And I guess my last question, going back to the last bit of your presentation. So you were talking about generalizing a policy. Well, I'm adding policy. Maybe let's go with that. Generalizing a policy to different objects, or to occlusion, or to things that are outside the field of view. Maybe deal with some active sensing stuff in the mix. I was wondering which representations for both making part of the observation space of the policy, or eventually conditioning a policy, have you been exploring, and which ones worked well, or which ones didn't work at all?
Yeah. So the question that we had, I guess still open, is that, so we're testing things like VLAs, right? So And VLAs were trained with basically some sort of imitation learning, right? You have like the expert trajectories, and they just like learn to regress that. So, but the problem, and what I think is a bit stupid, is that when you show them a new object that is basically the same kind of thing that you manipulated before, and then it's a new one that looks different, just because it looks different, the thing doesn't work. And I guess that one question that we had is like, how can we kind of still achieve, like learn what the robot should do regardless of the input, if the input is of the same class? So I guess that kind of naturally leads you to how can you decompose the scene into some primitives where you can get the abstraction, but then you can still learn the policy on top of that. So then there are like some works that we have seen. So for example, there was one, I don't remember the name right now, but it was one from MIT, from Leslie Cabling, and these people working on planning, and they basically proposed to do something like a VLA, but we're just using pre-trained models. But then it's more like you have a model that extracts the features. Yes. You extract the features, and then you have some layer that maps these features with the condition language plan to an actual plan that you can execute with, for example, an MPC or whatever. So, which I think it makes sense. It was extremely slow because the models are too big, but I think that it makes sense because I guess that you're decomposing the scene into stuff that you can generalize on. So, but I guess that was kind of my motivation to explore this alternative representation. So for example, at some point I want to add this sort of like layer in which you have the scene decompose into objects. Now I just have views, but the idea is to also decompose it into objects and maybe see if we can generalize from there. But I was like, first let's try with this simple latent space to see if it works at all, and then I can think about other hierarchies.